As I was saying, I'm ready to bore you guys again with the neglected tropical disease. I hope you would not get so upset. So, I added quickly the epidemic models aspects. I know many of us will know those things, but quickly, there's a SIR model, there's a flow in, flow out of the I compartments, and R naught is computed based on how much come in and how much goes out. That ratio, beta or gamma, is R naught. And if this is greater than one, the outbreak happens, and the R naught less than one, the outbreak doesn't happen. So the two main question we talk about, and it is called as an epidemic model, by the way, not endemic model, epidemic model. What determines whether the outbreaks will take off, how large will be outbreak, these type of questions we ask in infectious disease modeling. Well, not only that, but if R naught, the quantity R naught, which is a threshold, which is a ratio of how much coming in and how much going out, is actually tells you how large the outbreak will be, how quickly the outbreak will be. The larger the R naught, the quicker the outbreak and the higher the outbreak. So these different outbreaks that is shown for different values of R naught. We model it in a different ways depending on what biology we are trying to interested in, research questions, and what disease we are following. For example, susceptible, exposed, infected. Exposed is just infected but not infectious. I means infectious. SIRS, some diseases that you become susceptible again after temporary immunity. Recovered is a temporary immunity. You do the, some others you never become immune, you simply become susceptible, and those are things. Um, and then there are cholera type of disease where water, for example, environment play a very important role. So you need to put that environment into it. Then there is a treatment also sometimes is important. So you can put a treatment also in this. Um, and then this is called as an endemic model where you are incorporating birth and deaths. And these are all other ones where we don't have a demography. Birth and death is what demography is. That is called as an epidemic, only has one peak, deterministic model. And in the birth and death model, we have an endemic state. This does not have an endemic state. Okay.
So can I ask a question? You know, this R value that you talk about, it sort of seems like it would be, or at least from discussions around COVID, it would be spatially dependent. So, um, right. So how rapidly things spread might, for example, depend on the social distancing measures
Yeah.
and the density of the population and things like that. Yes.
Yeah, it depends on a research question. Actually, it's uh, I think Cindy was saying that a stochastic model is the most realistic, structured equation, age structure, spatial structure. All these are important, but I think this is what the modeler does. Modeler balance this thing, the complexity versus the research question or the point you have into consideration. That balance you have to maintain. So you're right. It is a matter of how population mix. Different population has a different type of behavior. Cultural issues comes into picture. So of course that is matter, spatial aspect. But again, if we are talking on an average situation of a country, usually in the news report, you don't want to hear confidence interval. Nobody take care of. Just talk about mean value, expected value. So I think we are lump summing everything when we modeling it, which is reasonable thing if you are considering a general idea about an outbreak. But if you want to go deep into one particular region policy, yes, that is true that we need to have a separate R naught. Absolutely true. And also the other thing is R naught is an initial parameters and it's not a later on parameter. Once the outbreak has started and people have realized there is an outbreak, there is no concept of R naught. R naught has no meaning then, because R naught is initial when the naive population, the outbreak is spreading. What would be the efficiency of the spread, basically? So those are the two main aspects of it.
Okay. But you can see why the public would be so confused by science then.
Right. Yeah.
uh,
Yeah, I think
Um,
the issue is also that we are quickly generating things with limited data. Data is so uncertain. Every day situations are changing. Even epidemiological situations are changing. It's not that we don't know much thing about. It's still, I mean, you see, outbreak happens in New York in last summer, but India has an outbreak. Doctors do not know in India what to do, even though there are published papers. Still there's so much of uncertainty there, because populations are learning, because the strain
mhm.
variants are different, the structure of the population is different, the way population behave to the outbreak is different. So it is unknown quite a bit before you can make a conclusion on it. So that's the conclusion. Anyway, and we are believing too much on prediction. Actually, I never do. I mean, I do prediction, but I have only few studies on prediction versus understanding the dynamics of it, mechanisms, how play it roles. That's the main task of these models. That is what I see it actually. Very simple. You are asking something?
No, I said thanks.
Yeah,
Yeah.
sure. Coming back to the point that Cindy was making, there is three types of models that I'm showing here. Go horizontally, row by. So the first model is SI model. You remain infected for HIV, for example. Once you are infected, you remain infected throughout the life. SI type model. The behavior of I compartment look like a logistic shape, S shaped. If you see an outbreak like that in the real life, this is the best model to model it. Um, but if you see a model like this, for example, flu, which has a peak and then dies out completely every season, because every season new strains comes into picture, SIR type model is better for that. But if you say the sustained behavior of little outbreak like COVID, which is having birth and death mortality is playing its role in the dynamics of it. So these behaviors are very, very simple, but it is the caricature of what we see in the real life that we are depicting in the epidemic models and going backward. So this is very, very interesting feature that. So the middle one is called epidemic model. The bottom and top one is called endemic models, basically. Actually, bottom one is called endemic model, basically, primarily because it is not a sustained oscillation, damped oscillation going to the steady state. Now, in infectious disease community, there are three types of stochasticity that they talk about. One is that they measure it in the data. When they measure the data, there is a measurement error, and they call it as a stochasticity. Another one is environmental issue, the climate factor, which is an external to the outside the environment model, which is called as an environmental noise or environmental stochasticity. And that is modeled in this equation, for example, a simple model that is where lambda is a function of different time. There is a different values of it with certain probabilities. And then demographic noise stochasticity also we talk about, and that is what Cindy was models that Cindy took into account was all demographic noise, where uh, there's nothing external noise, there's an internal noise. Why? Because if there is different, suppose there is a fish in the lake, some fish are laying 10 eggs and some other fish are laying 20 eggs. So the variation between the individuals are captured in this demographic feature, by the way. Demographic means population itself generating that stochasticity. Shin and I had a paper few years ago. I forgot actually which year was that.
Uh, three
Um,
years ago.
3 years ago, and we talked about vector-borne models, vector host model, very simple, and we tried to look into various way we can simulate it. Um, Now, as Amajit was talking about, we considered in his talk, we talked about population size, which is constant, fixed, a population size, which is variable as a parameter. Because, and then we talked about whether host population and vector population has some relationship between the two or not. And so we took it out different types of models and different types of boundary conditions on that. and kind of analyze this thing using functional central limit theorem and functional law of large numbers. So just to show you, this is very interesting, simple analysis, but it was very complicated when we did this part. And I think we wish to continue also, Shin, right? That is true in this
Yeah,
direction.
yeah, add a little bit more.
Okay. Um, Also, this paper that I published, so now I've talked about what I do. I studied ecology and the mechanism in which infectious disease spread. So, for example, we were looking at Ecuador, and there were that they don't know how many hosts are there responsible for the disease outbreak. And so we took a blood meal from we actually catch the sand flies. By the way, this disease is a leishmaniasis disease, which is spread by sand fly. So we caught sand flies in that area, and we dissected them and look at their stomach to find out the blood meal that they have taken, from where the blood meal is coming from. So what we found is the blood meal come from domestic mammals, but then also birds like chicken, for example, domestic chickens. So there were lots of blood from the chicken. And so chicken was not known before that the chicken is a host for this disease. But in this study, we found it is a host because these vector species is biting on the chicken, also on mammals, but also on chicken. In fact, they are biting more on chicken than in the preference for the chicken was more. Um, but it turns out, so that you can do it in empirical work, data. We collected the data, sampling data. But there you cannot tell whether this is a good host for the disease. So then we use our model, dynamic model, infectious disease model, to find out how good is the host as comparison to the other mammals in the local area. So it turns out they are, even though vector is preferring this thing, but the chickens are the bad transmitter of infection back to the vector. So this was the study point was, and very interesting work, both empirical and modeling work together taken into account. This another work was on Trypanosoma cruzi, which is Chagas disease. It is spread by different species of vector. It is called as kissing bug, Triatoma bug, and it is spread by different strains of the parasite, and many hosts are responsible for it. Now, Chagas disease is very common in Mexico and Latin America, but not common in US. It is there, but it is not pathogenic. The strain that is there in the US are not pathogenic, doesn't cause the uh, clinical symptoms, whereas in Mexico it causes it. There are multiple vector species, there are multiple transmission pathways. We are only looking at wild animal here, by the way, because in humans the prevalence is not high, but in wild animal these are the reservoir host, and that's why we are looking the cycle in that. So it turns out when you go deep into this study, it turns out there are three types of ways in which the host can get infected. Host can get infected by biting of the vector. Host can get infected by mother to babies, vertical transmission it is called. And the third way is by mistake, host eats the bug and they get infected. So there's three different ways these infection can transmit in this region. Very interesting biological ways in which the infection get transmitted. So we looked at the two different strains, and we looked at this region, region number two. Three is the dominant in one strain. One is dominant in second strain, different host, different vector species. In two, region two, these two cycles intersect because these bugs are now biting this host as well as this host. So that cycle's transmission cycle, which is distinct in three part and one part, is intersecting in the second part. So the question that we were addressing is the dominant strain in Mexico, can it overpowers the dominant strain in US? Because Mexico strain is very bad and clinical pathogenic, whereas US strain is not bad. So what are the conditions in which Mexican strain will dominate over a period of time in the US? That was the question, research question here.
Mhm.
So we took a simple model. So we consider only number two region, and we model it number two, one host, one vector, two strain. And we kind of look at the bifurcation analysis. There's lots of reproduction numbers here. Reproduction number is when the strains, one strain can persist, when the second strain can persist. One transmission pathway is there, the second transmission pathway means there are three that I talked about, right? So mother to babies, biting, and through the oral transmission by eating the bugs. So this is a bifurcation diagram. This is what we are interested in at the very end of the day. When can two strains sustain itself together, or they will outcompete the other one? What are the parameter regime in which we will have? So this region is showing E0 means none of the two strain will persist. E1 means strain 1 will persist. E2 means strain 2 will persist. And this is a bifurcation analysis, and bifurcation diagram is this one. This is what the end result is. So we can say if your R naught values are above this horizontal and this slash line, then strain 2 will persist. By the way, in this model, both the strain cannot persist. Somehow both the strain cannot persist. So that's the dynamics of it. That's the result of it, actually. And so if this situation occurs in Middle East, we can use the analysis for this one in Middle East. If it happens in Asian countries, we can use the same models there as well. Okay, so anyway, so there is actually, I will stop here because otherwise Shin will not have much time and Amber has to go. So I'll stop here. Thank you.
So Anuj, you actually need to be there. I mean, you need to be in the field to study
Yeah,
those disease
no, I go.
transmission.
I have a collaboration, and I go. I send my student also while when I was there to Ecuador and Colombia. We used to send that in the, and I was working with ICMR in India, Indian Council of Medical Research. Although in India I didn't do the experiment, but in Latin America we did many experiments on insects, on mosquitoes and sandflies.
No,
When you said you dissected the stomachs, you mean your team dissected the
Yeah,
stomachs?
no, we worked with some group in Quito, Ecuador, and they have an entomology lab. So our student participated in the lab, but they did it. They were just participating in the experiment because they are expert actually. So we don't know much about them, but we learned a lot in that because you see many times we read in the papers we don't understand what is critical from a blood meal analysis. Blood meal is the kind of dissecting and kind of finding out from their PCR that whether the blood is coming from cows or chicken or some or more. And instruments, knowing many instruments, there is sensitivity and specificity associated with the instrument that we overlooked many times, by the way. So
Neat.
right.
Shin, tell us something quickly.
Yeah, yeah.
Yeah.
Well, I think
Very-
there's two. There's more than one possibility. I hate Shin to rush. Just
Wait.
right.
Oh, just I only have a few slides, so don't worry, Amber.
Okay,
So
it's up to you. I was gonna say I could watch the video too.
it's
I'm
okay. It's
recording
okay.
it,
So
so you can always send the recording.
it's it's actually quite it's overlapped with many of the previous topics, so I think it's easy actually to go through. So I skip this. Oh, what's wrong? Oh, yeah. So I just want to mention I'm also working on queuing theory. I'm actually interested in the decision making in large scale service systems. But also I'm interested in the scaling limit theorems for epidemic models. I also do some time series analysis. So this is the work Anuj mentioned. So we look at a very simple, let's go to this picture, very simple so vector-borne SIS model, namely, so this is for the host. We only have two compartments. susceptible and infected. And for the vector, we also have two compartments, susceptible and infected. So what we do here is here. So we are going to fix the host population size, which is n. So that means we look at this closed population. And then for the vector, we actually have two models. The first one look at this random vector population size, but with a fixed mean. But as a special case, we also look at the fixed vector population size, which is assumed to be the C0n, which is larger. You can think of this as larger than the host population size. So the main idea is to study two actually different scaling cases. The first one would be we assume the host and the vector actually evolve at the same rate. And the second one, we actually consider the situation when the vector has much faster dynamics than host. That's reasonable because, for example, the mosquitoes or sunflies, they have much shorter life cycles. So our work, we need to identify the precise scaling in order to derive the functional law of large numbers and the functional central limit theorem limits. In particular, if we go through this flow. So if we look at just the special case when both the host and the vector have the fixed population sizes, that would mean, so this is actually for that situation. They both have actually fixed population sizes. So we can see that if you consider the same scaling for vector and host, so we are going to have this is a 2D system eventually. And we can look at this because 2D system just because you can actually just look at the infected process for both the host and the vector. So this is a two-dimensional system. Then we can derive the functional law of large numbers and the functional central limit theorem. That's actually quite standard. This is just for the density-dependent Markov chains. You just use we actually use just the functional law of large numbers and functional central limit theorem for Poisson processes. And then, but if we have a faster dynamic for the vector, then we can observe an interesting limit. So namely, we actually only have a 1D system. So namely, you can imagine because the vector actually involves much faster. So if you look at the time scale for the host, so this vector actually is in an equilibrium state. So in that way, the dynamic, so the random dynamic of this vector is averaged out. So we just have this one-dimensional limit, one-dimensional system. So this can give as a simplified dimension reduction. So this is so then we also try to look at our using the limits, look at the long time behavior, try to look at the approximate quasi-stationary distribution. Basically, we also use the OU process, the Einstein-Uhlenbeck process in our analysis. So this is just some rough idea. And then, so just from this study, so I'm thinking about some other diffusion approximations. So we know that there are two well-developed diffusion approximations. One is just the central limit theorem, namely also known as the linear noise approximation. So this is basically what you do. First, you're going to get the deterministic limit. Then you look at the deviation of the system from this deterministic limit. You look at the normalized deviation. You try to derive the central limit theorem. So this is called the functional central limit limit. Now, the other one is called the Langevin approximation, which is exactly what actually Cindy mentioned. I think here I just want to actually distinguish from the functional central limit theorem. I call it the Langevin approximation. So let me just give you some more details. But before I do that, we know that if you just look at the functional central limit theorem, This actually look at the linear, kind of look at the linear fluctuation, because you look at this difference. And on the other hand, if you look at the Langevin approximation, it actually can capture the nonlinear fluctuation. So in this sense, it actually behaves better than the functional law of large numbers and the functional central limit theorem. So here I actually try to look at the recent work by Ruth. So this is actually the some recent work by Ruth Williams and her co-authors in 2019. They look at the chemical reaction network. They also consider the Markov chains, so continuous time Markov chains. But they try to develop these constrained Langevin approximations in the sense that because the number of molecules are non-negative, so they actually put a reflection whenever this process actually reaches zero. In that way, so this Markov chain actually stays in the non-negative orthant. Now I'm thinking if we are going to have the same problem for the epidemic model, I think we do. So here I look at a very, very simple SIS model with a closed population. So that means you only have one-dimensional process. So here I look at the infected process, which is denoted by IN, which is the number of infected individuals at time t. And this N is the population size. So this is the equation. So just like Cindy mentioned, you look at the input, you look at the output. So this input is from the susceptible compartment. So this beta is the transition rate. So you do have this quadratic term because you have the closed population. So N minus INS gives you the susceptible individual number at time S. Now this is actually the recovery process. The gamma is the recovery rate. So then this is the Markov chain model. And then we just used the this Tom Kerr's paper back to 1978. So for any unit rate Poisson process, you can actually construct this Brownian motion. So this is standard Brownian motion. Write it down in this way. So look at it. This is a log t, and this is a lower of a lower order. So you can imagine that after the scaling, if n is large, I can get rid of this lower order error. So in that way, if we consider the scaled process, which is the proportion of infected individuals, then this can be approximated by this SDE. This is exactly what I think Cindy wants to write down in that whiteboard. Maybe similar. So in that way, you can see the drift is just the combination of the two drifts. So let me just go up a little bit. So this this drift minus this drift gives you the C. And for the standard deviation, it's just you can think about the variance. Variance is equal to this variance plus this variance. Then you take the square root. So here I write it down. And okay, so Amber only has 1 minute. So I probably cannot finish in 1 minute. So I can try to repeat this tomorrow morning for Amber. But let me maybe continue right now for the others.
That sounds great.
Yes.
Or if it's on the video and I can somehow cue to that spot, I could also watch.
Yeah,
so.
I think it's interesting. So yeah, we
I would like
to
see.
yeah.
Okay. Yeah. Thank you for understanding, and I do apologize for being difficult.
No worries. Yeah, see you tomorrow. Yeah.
Yes, we'll see you tomorrow. Yeah. Enjoy, you guys.
So this X is called the Langevin approximation, or people just call it the Theorem approximation. You can see that here we do not need to look at the deterministic limit. We directly have this SDE approximation for the Markov chain. And then the problem happens at the time when this process actually reaches 1. So you can see that when this x is equal to 1, so the drift is actually negative. So negative gamma. So if you plug 1 into this drift, you are going to have a negative gamma. But if you look at the sigma, which is the diffusion coefficient, if you plug a 1 into this sigma, you're going to have root gamma here. So this root gamma is positive. So this white noise can certainly let you outside this 0-1 interval. So because here we look at the closed population, if you look at the proportion of infected individuals, you must have some number between 0 and 1. But this white noise could actually pull this process outside this interval. So although this drift is negative here. So this actually make me think, can we also develop some constraint Langevin approximation for this I bar and T? So that means we actually want to put some reflection at this 1. So whenever this process want to actually escape from this 0-1 interval, we are going to give it a pushback. So that's actually what make us think, okay, now let's actually add this additional term. So we call it L. So we call this process, we call it a reflected SDE Y. So the Y is defined in a very similar way to the X process, except we're going to add this term. This is very similar to the construction of the reflected Brownian motion. So you can see the initial is still the same as the initial for the original infected process. The C and the sigma are the same as before. And now this L will add this minimal pushing effect, actually along the direction -1. So because now you are going to add this effect at 1, you want to keep your process less than or equal to 1. So this is along this -1 direction. Now here, so following Ruth's paper, I think this LT can be written in this way, just using this drift. So because this is C, this drift, if you come back, so let me come back to this drift. If you let X be 1, now you're going to have a negative gamma, which is a negative direction. So that's how you construct the L. So now you can see that we have this reflected SDE approximation, or we call it the constraint Langevin approximation. This is the name Ruth actually used in her papers. So now I want to actually.
So Shin, why is indicator bias in both 0 and 1? I would have thought reflection is only when you are at 1.
Yeah. I don't know why I write 0 here, but if y is equal to 0, the C is equal to 0.
Oh yeah.
Yeah, so it's okay, but certainly I should write down y is equal to 1. That's actually clear in So,
okay.
Right. So here now using this constraint Langevin approximation, we're going to have a lot of new questions now. So for example, extinction persistence, namely, for example, Amarjit, you mentioned the quasi-stationary distribution. So even for this simple one-dimensional process, can we prove that there exists a unique quasi-stationary distribution? And also, we may ask some other questions like what Amarjit did in their paper. So, for example, as n goes to infinity, would you have this kind of like the interchange limits? So, namely, you let n go to infinity, you're going to reach this reflected SDE process. If you let t go to infinity, given this process will not reach 0, you're going to reach the quasi-stationary distribution. But do you have the interchange? Because we believe that for the original Markov chain model, you do exist this quasi-stationary distribution because you have a finite state space and you have a 0 at the boundary point.
I think you will have a unique quasi-stationary distribution for this model as well, because you're in a compact state space and you have, I imagine sigma is, sigma is not uniformly non-degenerate. It is kind of getting closer and closer to zero, or is it uniformly non-degenerate? sigma is, I guess you can give a lower bound. No, no, when x is close to 0, it gets smaller
Yes,
and smaller, right?
smaller and smaller. Yeah.
So that may cause some trouble, but I'll be surprised if there is not a unique quasi-stationary distribution for this model. For
This is certainly the simplest one.
yeah,
Yeah.
yeah.
I haven't looked into the technical analysis of the long time behavior, but I think I'll be interested in the future. So as a future work, or so look at the property of such constrained Langevin approximations for epidemic models.
So here, of course, you just considered something which is in an interval. I mean, but in general, multi-species or multi-dimensional models, you
Compartments.
will have orthents, right?
Yes, exactly. Yeah.
Or simplexes, simplicity.
Mhm.
Well,
Yeah.
in that case, that boundary would be more like planes.
Yeah, yeah, it will be like the
Yeah, cubic.
boundary of an
Well,
orthent.
an orthant.
Right.
And some other thing we're interested would be, so so if you look at the multi-scale epidemic models, just like what we studied, like the vector-borne epidemic models, you're going to have fast and slow scales. So the question now, can we also develop such Langevin approximation for the multi-scale epidemic models? Because when you look at the chemical reaction literature, basically Tom Kurz actually has a series of papers studying the diffusion approximations and fluid approximations of the chemical reaction network. But they actually use the functional law large numbers and the functional central limit theorem. They didn't actually came up a way to directly derive such kind of approximation. And also they kind of mentioned that they cannot do that.
So I have a question about, when you say we develop this approximation, I mean, is there a rigorous limit theorem which kind of connects the
Yeah,
original system with this system?
yeah. So this is actually now that so this is actually in the work, the first paper,
Hmm.
the Leach and Williams. So that paper is in the published in Annals of Applied Probability. They
Mhm.
provided a systematic way to construct such kind of constrained Langevin approximations for the chemical reaction network.
No, but my question is this: if you look at your approximation that you wrote, there is an
Mhm.
n there as well, right? In
Yes,
the equation, there's an n there as well. So
yes,
in what sense this is an approximation of that? Means how do you
yeah,
make sense of that?
yeah. This is a good question, and also I borrowed the idea from this paper. So what they do would be, they're going to split. So they're going to split this two Poisson processes into two parts. One part is for this Poisson process in the interior of the domain. So you simply add this indicator inside this each Poisson process,
Mhm.
and plus the Poisson process on the boundary. Again, another so indicator function inside the Poisson processes.
Mhm.
Then they're going to keep this Poisson process in the interior of the domain, and so that's the same, unchanged. But for the boundary part, they're going to introduce this parameter r. So this r actually is equal to, I think is equal to n inverse.
Mhm.
So they're going to separate these two parts and kind of actually only look at this boundary part.
Mhm.
So they introduce this new r. They're going to let this r go to 0. So that means in the limit, you still have the n,
Mhm.
but the
Mhm.
n is kind of fixed.
Mhm.
So instead, you're going to have the boundary part actually go to limit.
I see.
For that part, the n disappears because you're going to replace all the n by r.
I see.
I would think this idea can be used for the multi-scale system. You can certainly do this. I mean, you fix n, and you're going to look at different different time scaling.
No, it makes a lot of sense.
Yeah, this is about some of my projects. Yeah.
Okay, so what do we do next?
I think we can collect some finer thoughts that we have many things we discussed. We can make a quick notes on what are the topics we want to carry forward. There's so many things, but maybe 3, 4 of them as a final thing we carry forward, and we discuss more details tomorrow morning on that.
Yeah.
According to our schedule, we should summarize the important points from today. Or yes.
Yeah,
But
I mean, yeah, there's
Yeah.
lots of things.
Yes, and I started to do that at the beginning of my talk.
Yeah, I mean, there are lots of different things. I mean, sometimes it takes a little bit time to synthesize the common ideas.
Yeah.
But I mean, it seems like somehow many of us are thinking about some type of scaling limit type of behavior, which can be interpreted in different contexts in different ways. And that is a theme perhaps we want to come back to, and maybe try to identify something which is interesting and relevant to the epidemic modeling problems.
Yeah.
Yes, scaling limits are always there, and I've come to think of them as an intermediate between the discrete model, discrete space-time. Okay, and then there's scaling limits. And then when we compute, what we do is we take our scaling limit and we discretize.
Yes.
And an interesting general mathematical question arises in the form of, can we just skip that scaling limit?
Yeah.
I mean,
although the idea somehow is that
sounds unfriendly, but I mean it in the best possible way.
No. So what I guess what you're saying is that usual game is this: you have a very complicated model, and you take a scaling limit, and it gets simpler, but then you discretize it to do some competition with it. And so, can one go from a complicated, discrete model to a simpler discrete model directly without passing through the scaling limit? I think that's certainly.
Yes. Something else that I'd like to say is that I'd love to see us put all this technology to work on some particular problem of Anush. Now he's given us a large variety to pick from. I've actually worked some, although I don't think anything's published on malaria. I know the life cycle of some kind of mosquito, and what happens in the human gut, and so I have a taste for this sort of stuff. from that experience. Yeah, and why not focus on one of those this time? May at least to the extent of the vector the vector aspect is included. Actually, I was wondering if in the present epidemic that we know and love, if we could model our children as being the vector.
So Anuj, can we go back to your morning slides where you refer to this one paper which came in PNS or PNS towards the end of your talk? Um,
You were talking about
As in the
the
mailer.
morning slide, right?
yeah, morning one.
Yeah, so this was the work which was
Oh,
awareness
this
driven
one.
behavior, which was trying to show why there is a difference in the type of peaks if the behavior can explain this different types of peaks. Uh,
No,
was
no,
it that?
there was another one where you had this rate equations with the D's and so on,
This is the
nonlinear
hop.
equation.
This is the mailer Hopper.
Yeah.
Oh, okay. This one you were talking about.
Uh,
This one?
So the two hosts.
does it
That
have
one.
D's in it? I remember it had in the denominator there were some D's.
Oh, I
Uh,
think that's
Oh,
the
yeah,
one.
yeah. It was this one.
Awareness. That
Yeah,
one,
it was
right?
awareness one. This
Yeah,
was
yeah,
the
yeah,
one
yeah.
I was talking. Yeah, this is a good one.
yeah, this one,
Yeah, yeah, yeah.
exactly this one.
Yeah, yeah.
Yeah,
Yeah,
and
yes.
this could be made simpler also. I mean, I could make, see, there is two things here: short-term awareness and long-term awareness. Short-term is by this little delta over delta C, and
Yeah.
long-term is over D over DC. We don't have to take both of them together. We can take one by one, for example. It will make it much simpler from that perspective. And
So this one, they didn't look at any stochastic models, right? They just looked at the ODE models.
yes, just all deterministic.
Yeah. So I could imagine that this, this the sustained behavior that one is trying to capture could also be captured through some kind of stochastic model, and
Well,
just like Cindy was talking about, right?
Uh,
Means
so, so Cindy was talking about endemic. If we add in this birth and death, if we add in this birth and death, what Cindy is having, we can get it in a stochastic model that is sustained. Is that right, Cindy?
Yes, yes, but uh, but then the birth and death become a function of t. Those rates, need to be a little bit more free to vary. Yeah, is that right, Anuj?
Say it again, Cindy. I couldn't hear you very well.
You were saying like putting in demography, but then this demography needs to depend. The rates need to depend on time in order to get back to your.
Well, it could be we could make, or we can do one thing. Actually, you need an endemic state actually. So what we can do is SIRS.
Okay. Yes.
RS. So
Yeah.
we do that and notate them
Yes. Yeah.
octavely, and then we can have a steady state.
so
Uh-huh. So can we do that with the vector?
Sure, we can do it, but the point is that if we do the vector, we will add two more equations.
But we know how to look at subsets of our equations. We know how to dimension reduce.
Right. The
Well,
paper that with Jen, we did the same thing. We kind of isolated human to vector
yeah,
equation, so we separated it out. Yeah. So
yes. So with multi-scales.
yeah, with the multi scales.
so what about Cindy, the type of analysis you did with Peter Baxendale for this type of a model where you kind of extract a slope process and
Yes,
uh,
this works. This works in the simple form with Baxendale, it works any time you're willing to look in a linear neighborhood of a fixed point. And then you assume you have complex eigenvalues, and the rest of the thing goes.
That will have, Amarjit, that sustained oscillation and the scales that you are talking about.
Yeah.
The Cindy's work will have, this model will have that.
I see.
Yes, that's true.
I see.
The only thing is that Cindy's model is probably 3-dimension, I think, 3 or 4-dimension.
No, it's 2.
It's 2-dimension.
It's 2, and then Amarjit asked if you can do it higher dimension. And yes, but basically it's 2.
So I think one compartment we can remove is the E compartment here. E compartment will be completely gone. So S, I, R, H, and D will be there. D will impact actually. D is also impacting this thing, the equations. Yeah.
Yeah, I fully don't understand right now the reason for trying to eliminate compartments. Why do you want to do that? I mean, just to make the model.
In order to get sample path results.
My guess is that it will be a little complex.
And it happens naturally because we've been talking all this time about modeling, but we haven't been focusing on what questions do you actually ask, what answers will be useful. Mm-hmm. And often you're asking a question which is not actually a question about the whole process, although you have to know the whole process in order to get the answer, but the answer may be in terms, in such terms that you can use a reduced model.
One thing I want to show in this model, this is actually a very beautiful model. By the way, this is having, Cindy, this having an oscillation in it, as you can see on the top left.
You bet I saw that immediately.
And there's one thing which is very interesting in that, and that is the second bullet on the right-hand side, second bullet. An extension of SER with lags between infection and fatality. Lags between infection and fatality. Now, this is very, very important point here. What it is trying to
this would be a phase. This would be a phase change
actually
in the damped oscillation would be a phase change.
Well, my guess is this lag is generating that oscillations. My guess is that.
Oh, it's actually a time lag. Yes, those things. That's another whole subject to itself. Is the analysis.
Yeah, let me say something.
The analysis with phase lags, it leads to oscillations.
Yeah.
And it's a different, like I said, the flow K theory is a different piece of real analysis. And so is this.
Cindy doesn't have a T. We don't probably may need, this is not explicitly depending on time, by the way. So right-hand side does not depend on explicitly on time. So maybe we might be okay with this simple theory, a simple analysis of bifurcation aspect. So the reason it generates the oscillation is because of following. You know, if you have a SIR model and you have a quarantine compartment, quarantine is that the people are quarantined for temporary and then thrown back into the system after certain days, right? So what that generates, it sucks the people and brings it back. And that generates an oscillation in the dynamics in certain parameter regime. My guess is that lag here of infection is impacted by the mortality here, is causing that same phenomena that we see it in the quarantine compartment. And therefore it is a generation of. So this is, they have not done any mathematical analysis. They have done very simple analysis. So I think it would be quite interesting work from both bifurcation, stochastic analysis, and an application perspective. Application will be also very solid here.
Sounds good, and I would love to understand that point. I'd love to see the analysis, actually. And you say they don't have it, really?
No, they don't have it. Their main point was to do numerical simulation and make a point. Their question is very novel. The question is very novel, and that is novel question is, how do you explain these peaks, which is sharp rise, but not sharp decline? Some sharp decline, some not sharp decline. So why is that so?
So what function is it that has this peak?
This is a daily deaths. So this is capturing D, capital D.
Oh.
D compartment. This is a D compartment, deaths rate, reporting death.
The death rate is a function of what?
Oh, so death rate here is just people who are dying are getting collected. It's a linear function of hospital. D dot is hospital. People who are dying in the hospital are coming in the death compartment here, right?
Yes, but it's a dynamic in T, is it?
Yeah, it's a derivative, dd by dt. Dot mean there's a dot on the top. I don't know if you can see.
Oh yeah, I can see it, but okay.
So the dynamics is coming from H dynamics is coming from I dynamics is coming from the transmission term. The transmission term is the nonlinear term that is generating the dynamics.
So the right-hand side is constant, or H is a function.
H is a function of time, right? H is a variable.
These are just ODEs, right? So
we
have
okay. H is a
five-dimensional ODE, and for S, E, I, R, and H, and then you put H on the right-hand side and you get D.
Right. So I think there are 3 to 6 variables total, including D.
Okay. Yeah, I see that now.
Yeah.
And so I mean, so I think there are different directions to go with this model. So, for example, Shin's idea of trying to write, principled diffusion approximations for the jump. So you can write jump processes, corresponding to this model, for example, which would be the stochastic models describing this. And if one wants to think about, how you describe deviations around the ODE, then the natural thing to do is to write down these diffusion models. This Shin's idea of, somehow making sure that, they, respect the constraints could be useful there as well. So one could, maybe this model could be a starting place for developing several different things, depending on which direction we go to.
Precisely. And that could be a good work, because this 1 week at least we set up the research questions that we can focus on. Would be quite a good progress, and if we start to work on that direction. So there is a damped oscillation, then there is a lag generating an oscillation. Lag is generating an oscillation. My guess is this. The sustained oscillation aspects has 2 frequencies kind of interacting with each other. And then if you add a stochasticity, there is another frequency. So 3 frequencies kind of.
No, stochasticity doesn't add a frequency.
It will
No,
generate.
what stochasticity does is it turns a damped frequency into a sustained one.
Yeah, it just somehow.
Yes, it's
amplitude.
Some people talk in terms of filtering, so that this set of ODEs has it's like a filter which filters the frequency out of the noise. This is how engineers talk.
Yeah.
But the frequency is there already. It's intrinsic to the deterministic model. Yeah.
I guess we should bring in Yunnan. His theme, is certainly relevant to what we are doing, but maybe he's.
Yunnan,
Yeah,
where
I'm
are
here.
you?
So, I mean, it will be interesting, to bring some of your problems in, even if this problem doesn't capture it.
I think
Sure.
Yunan's point, Yunan, if you may allow me, I would connect your problem with this one.
Of course, please.
So I worked on a problem of diagnostic testing for COVID.
Okay.
So in COVID, what happens is there is a rapid test in the market. Rapid test is a quick 15 minutes, half an hour, you get the test result. And then there is a PCR test, which takes like few days to get the result back.
Mm.
So that's where this thing becomes very important.
Good point. Yeah.
And then you take into account healthcare system also. You see hospital testing, which is still part of it, but it's kind of adding, but you have to use it as people who are having mild symptoms or flu-like symptoms, which they don't know whether it is COVID, flu, or cold, or some other virus, right? And they go for testing, and some will have correct testing, some will have wrong testing. The wrong testing, a person, if has the infection, will go in the community and infect it. Okay.
I see.
And that's how we will connect it. In that case scenarios, what you are thinking in mind, SEIR model, can be very well fit into your healthcare.
I see.
Yes.
So
yes.
So the service capacity. So in my model, I sort of model the service capacity refers to beds, but you're saying service capacity should be the testing capacity.
That could be the case. Yes, that could be the case. Yeah, that could be the case.
I see.
Because we are we are in an emergency situation. We don't want to put someone in the bed if the person is not COVID or any serious issues, right?
Right.
So we want to also isolate that person immediately, even if it has a mild symptoms, if we have an empty bed, because otherwise that person will go in the population and spread maybe a super spreader.
So you have two types of treatment. I mean, in testing procedure, one has a quick turnaround time, the other one takes a longer time but more accurate.
Right.
Interesting. So you have a trade-off between quality and time, efficiency.
So it's a rapid, less time, but more inaccurate.
Okay.
It is faster, taking time, and accurate, gold standard.
Very, very interesting. I see.
Okay, you are happy?
Yeah, definitely.
So,
I mean, this is what we're looking for. I mean, we're some theorists, and we're looking for real problems to solve. so I mean, I think, a lot of insight.
Okay.
Yeah. I thought Yunnan's, let's say, model or discourse, I thought it was the closest to something that we could just pick up and work with.
Well, I think as far as I'm understanding,
he's already taken some of the steps, as you just pointed out.
Well, maybe maybe my steps are in the wrong direction. I'm just,
well, no, it's relabeling. It's a not too difficult translation, and then some of the details are different, but the core of the thing is very similar. So similar one can leap from one to the other.
Yeah.
So Anuj, so in this problem, what is your decision here? Capacity planning or scheduling? Uh,
Well,
yeah.
it could be multiple objectives. It could be multiple objective. You see, even bed planning is associated with it.
Okay.
Uh, you see, you don't want to overwhelm the beds by patient who will turn out to be not a severe patient, or,
Right.
or because the symptoms are very same for all these diseases like flu and COVID, you know, and
Mhm.
so it is very important. And also, you want to quickly isolate if it is a COVID, quickly
Right.
you want to do
Right.
it, even if it is a mild symptoms, especially when
Right.
you have the capacity. So of course we have to think on the objective function, but I can very
Okay.
clearly see different objective functions there. I can clearly
I
see.
see. So a quick step maybe to consider maybe two class customers. One are just non-COVID, the other one is real COVID, but you don't know it.
Yeah,
So that's
well,
some probability. Okay.
yeah, there is something technically called as sensitivity and specificity of the test. So when a patient comes, there is because none of the test is 100% perfect. So you may sometimes get a patient and you test it, that a patient has the test and you test it. A patient has the virus and then you test it wrong,
Mhm.
or patient doesn't have it and you test it incorrectly, that the patient has the virus. You know what I'm
Right.
saying?
False
Yeah.
positive.
Yeah, Yunnan, did you ever have a statistics course?
Some
So you
long
heard
time
of,
ago.
did you hear of type 1 and type 2 errors?
Yeah. Yeah. False
Okay,
positive.
that's what Anuj is talking about.
Right. False positive. False negative.
Yes.
Yeah. So
Well,
both are undesired, right?
yeah, the
Right.
point that we are discussing, Yunan, is that
Yeah.
this model can easily be adapted to your framework of queuing and capacity building. But we have to think over the objective function. That is what I'm trying to say.
Wow, this is beautiful. This is so great, sirs. I think we already have some ideas today. I mean, one day we have already have some ideas.
Oh,
So
yes.
productive, so good.
So what's the structure for tomorrow and the rest of the week? What are we going to do? How are we going to do it?
I don't know.
Well, I think Cindy and I have organized before. And Cindy, would you like to say a few things, or I say something from my experience?
I want to say that I don't want to break into subgroups yet.
Okay. Yeah, well, we are short group, so we don't have to.
We need, yeah, we might not need to work in subgroups at all, but yeah. Okay, so another thing is I'm concerned that Yunnan is not appearing on our screen. I don't know why it's Yunnan, maybe
Oh,
because
sorry. I had to turn off my
No,
video. I had to
it's-
go to the daycare and pick up my son.
It's-
So I'm the
it's a-
only driver at home.
it's a different aspect. It's that when we're sharing screen, we have only 5 spots. There are 6 of us. And I have been missing you
Oh,
because
sorry.
you have been the number 6 not there. And so I've been thinking, how can we fix this, to share around and not have you be always a missing person, which is not good.
Yeah.
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 And so coming back for tomorrow. So what are we doing tomorrow?
Maybe we can finalize this. This is one idea. This is one idea of moving ahead with this type of model, which has a short-term awareness and long-term awareness. And then we kind of write it down what the model that we wanted to further analyze it. And what are the research questions? As Amajit, you were saying, there are different aspect of things that we can answer, including one more aspect, which is Yunan's point, is adding an extra queuing problems with this type of framework. So there is a few extension or few sub questions to the same piece.
Yeah,
Basically.
So this paper you have in the Dropbox, right? The paper on which this.
Yeah. Yeah, this is coming from this paper actually.
Okay, so yeah, so maybe we could
And my slide is also there. My slides are all there in the online. I think, yeah.
you
Is my
certainly
slide
sent
there?
it to us by email.
It's it's
Can
actually already in the Dropbox. We can try to create a different folder which collects all the presentations.
Mhm.
Yeah, that will be a good
That's a
idea.
good idea.
Yeah.
Well, there's one missing. What was the very first one?
It's okay.
Yeah, I can put my slides in that as well.
Yeah.
Yeah, that's right. It was Amarjeet.
And also, Cindy's write-up is we can take a PDF on that PDF of that file where Cindy was writing on the what is that called as?
This is not meant for posterity.
No, you were writing something, right? In
I-
the what is it? That software? I forgot the name.
Scribble.
Scribble.
Scribble, scribble. That's what it was too.
Upload image.
Yeah. So as a format, I suggest that one person should write on the board and other people should suggest what are topics or something. We should have a list of priorities and everyone gets to say what are their priorities or something like this, so
But
that we get an impression
tomorrow,
of,
right, rather than today.
yeah, not today.
Yeah.
No, as a way of starting off tomorrow so that we organize and get some momentum going first thing in the morning. And do we meet at 8 o'clock? Yes.
I would
8 or 8:30.
8:30.
I would hope we can maybe have a longer lunch break, because for today, many of you actually didn't have enough time to grab your lunch, because Amber is not going to teach on Tuesday. That's my understanding.
So can we start at 8 and
Yes.
have the, yeah, so could you put a
I'm going
notice
to
out so everybody knows that, Shin?
So
That we start at 8 and then have the, on Tuesday, we have the original schedule.
yeah, that's what I hope so. So we start at 8, then we have 1 hour break at 10. That's the Pacific time.
Yeah.
And then we have another break at 1, again, the Pacific time. And then I'm going to send this so by email, try to remind Amber. Yeah.
Yes, and then another thing we need is where do we meet? So you Shin, again, send your
Zoom, my Zoom link. Yeah, that'll be fine.
Your Zoom, yes, so that we all know where we're meeting.
Yes.
Where and when.
Yes. So we are going to do a summary tomorrow morning, right? The first thing we need to do.
Yeah. Well,